space, we have the sun. It's spinning. Everything is spinning to some degree. Some asteroids spin more than others. You have the afternoon side of the asteroid. That is the spot where it's the hottest. So there's the most infrared light coming off the asteroid at that part. On the night side over here, it's relatively cold. Less infrared coming off the surface. Infrared heat is also, photons are also light. They carry momentum. It's not balanced, so there's more pressure being exerted this way due to there being more photons going off in the opposite direction. Newton's third law, there's an equal and opposite reaction. More photons go out, the asteroid gets pushed the other way. The key point about the Yarkovsky effect is that it depends on the direction the asteroid is spinning. So we have the asteroid spinning. If it's spinning one way, it gets pushed forward in its orbit, and its orbit eventually expands. If it's spinning the other way, retrograde rotation, it gets pushed backwards along its orbit, and the orbit eventually shrinks. So there's this complicated interaction between the asteroid's size, shape, and density, which determine how much the Yarkovsky acceleration is, and the direction that it's spinning, which determines the direction of that push. This was first detected in terms of actual application. Early satellite work, there was a project called ECHO. They launched a large balloon that was aluminized on the outside, inflated orbit, and you could bounce radio signals off of the balloon. The balloon kept moving in ways that they had not expected, because radiation pressure was pushing it around, and thus the Yarkovsky effect has been observed. Now, the balloon has very light weight. It's very thinly spread gas inside. Rubble pile asteroid density is typically at least out of water, although some are just a little bit less because they're fairly porous. Very heavy, and yet with very careful observations, particularly the radar astrometry we can get, we can measure even 1 kilometer wide asteroids getting pushed around a few kilometers over a decade or so of observations. So we're seeing rubble piles the size of mountains getting chucked around just by sunlight shining on them in different ways. So that was kind of impressive. The last maybe 15 years, we realized something else, which had been suggested theoretically, again, long before. And this is the Yarkovsky-O'Keefe-Radziwiecki-Paddock effect. We will call this YORP. So if we have an asteroid, if it's a perfect sphere, then this is Yarkovsky's model. But asteroids aren't spheres. You saw just how irregular they can be. Even if something is overall shaped as spheroidal, it's going to have piles of blocks all over the surface, probably. So these irregularities mean that the net effect of this X-ray heat coming off can be offset from the asteroid's center of mass, so it can get a torque. So not only is it getting pushed, it's getting spun up or spun down. So how does this work? This is a binary asteroid called 1999 KW4. I apologize for the telephone numbers. With so many asteroids, it would be a pain to think of hundreds of thousands of names. But Steve Ostro, who is my thesis advisor one of my thesis advisors at Caltech, observed this system quite some time ago now, and realized that KW4 has a couple of interesting properties. One, it has a satellite orbiting around it. So we have a large asteroid and we have a small asteroid around it. And two, it has this big bulge around the equator. Where did that come from? Well, consider the YORP effect. We have a pile of rubble sitting in space. We keep spinning it up and up and up and up. Eventually, it's going to bulge out around the equator. The Earth bulges out by about 1 part in 300 because the Earth's gravity is quite large and the Earth isn't spinning that fast. We take a very small asteroid, we spin it every couple of hours, it's going to bulge out quite dramatically around the middle. Now, if it's a sphere, roughly speaking to begin with, if it was a pure fluid, it would act like the Earth. It would become an ellipsoid. But these are piles of rubble. The fact that they have compressive strength and internal friction starts to matter. And you end up just bulging out material around the equator and getting an actual ridge as opposed to a smooth ellipsoidal shape. You also can get various irregularities. KW4 is pretty much round around the middle, but there are other asteroids where we see large dents in those equatorial ridges. It's not clear if those are impact craters or if it's just we spun up this asteroid and bulged it out, and The arrangement of blocks on the inside happen to give it that shape. As it spins up and up and up and reconfigures itself, we have another complication. I talked about how York depends on the asteroid's shape. The shape just changed. Oops. Now all the York torques are different, and so there's this complicated sort of random process where asteroids spin up over tens of thousands or hundreds of thousands of years, reconfigure themselves, and then may either keep spinning up or spin down again. If they keep spinning up, eventually material at the equator goes into orbit. So the asteroid literally flies apart. This was the original suggestion for York, called rotational bursting. The idea was that asteroids would spin up so fast that they would actually explode. That relied on the object having enough tensile strength that you could spin it up so quickly that when it broke, pieces were traveling so quickly that gravity couldn't hold them together. If it's a rubble pile, very loosely consolidated, you can sort of shed off material and form a moon, and it will stay in orbit. And maybe 15% or so of asteroids a few hundred meters wide, the Earth objects anyway, have satellites like this. So that's pretty cool, I thought. So this is all very interesting and unusual physics, but what does this have to do with the Earth? This is where the danger part of the title comes in. It may seem a little bit overblown, but it could have been worse. Luis and Walter Alvarez, who used to be over at